In today's lesson, we're going to be continuing our study of discrete random variables and their probability distributions. And in particular, we're going to be introducing the concept of expected values. Now, expected values are sort of implied by their name. It's going to be the values that we expect to observe when we start observing a random process. They're going to be very much related to the measures of location and of spread that we were looking at in our descriptive statistics portion. And we're going to first look at them related to discrete variables, and then again, we'll re-explore all of these ideas as they relate to continuous random variables when we get to that point in the course. In today's lesson, we want to define and then understand what the expectation is and how it's computed. We want to understand some properties of the expectation or the expected value, and I'll be using those phrases interchangeably. We also want to define variance and understand how it's computed, and understand the properties of the variance. Now note, when we're talking about variance here, this is going to be distinct from the variance that we were looking at the start of the term, which was the sample variance. And so this is going to be a property of the population rather than of a sample. So we can start by thinking about this idea of gambling, right? And of thinking about, what do you expect to happen if you start to gamble? And one of the games that's easiest to understand when we're at a casino is the game of roulette, right? And so roulette has several different squares. All of them are red or black with some exceptions, and they're all numbered. And then you can come up and you can place a bet. And the simplest bet that you can place is whether you want it to turn up red or turn up black. And there's a roughly 50-50 chance of each of these things happening, right? And so if you were to go into a casino, you could decide to bet red on every bet or black on every bet, right? And in about half the cases, you're going to be right. And so it seems like, in the long run, you could continue placing these bets. And if it really was 50-50, if we were really flipping a coin, then in the long run, you're not expecting to win any money, but you're also not expecting to lose any money, right? Every time you're going to win some, you're going to lose some with equal probability. And so you can sort of do this indefinitely. But on a roulette wheel, they put at least one of these green squares. And what happens if it turns up green is that if you've bet red or you've bet black, then you don't make your bet back. And so the probability is actually going to be slightly less than 50-50, red versus black. And so instead of expecting to sort of be able to stay even in the long run, when you're actually playing roulette in person, you're going to expect that over the long run, you're going to start to lose money. Because even though it's very close to 50-50 odds, it's not quite. It's a little bit less than that. And so if you keep betting, as more time goes on, you're going to continue to lose money. And this is sort of true of any game at a casino. The casino is always going to be the one that wins the money in the long term. But this sort of captures this idea nicely of, while any event is possible, while you could walk in, put a bunch of money down on a roulette wheel and win a lot, our expectations are that over the long run, you're going to wind up losing your money, right? And so how do we capture that idea mathematically? The expected value is the mean value of a probability distribution. So it corresponds to the value that we saw for the sample mean, and there's sort of the population value is the expected value, and the sample value is what we were looking at before. If you were able to run an experiment infinitely long, and then you actually take the sample average, that's what our expected value is going to be. So we're going to be converging to some value in the very, very long term, and that value is going to be the expected value. Now, in general, this is not going to be the same as any sample mean, right? When you actually observe a sample mean, you're not generally going to observe the true expected value. But as our sample size gets really big, we're going to expect to get closer and closer to the truth. We write down the expected value of x as e of x, right? So this function e applied to x, and we calculate it as this summation here, right? So we take the summation over all possible values that we can take on for our random variable, and we take x times by the probability that we observed x. So here our script x is the set of all possible values for x, and we're assuming that p of x here is the probability mass function for x. Right? Now, known distributions like the Bernoulli or the geometric will often have closed form expressions for their expectations. Now, just to give a quick example here, let's say that we have a random variable, right? And it's going to be our x, and we're going to say that x can take on a value of a 0, 1, or a 2. Takes on a 0 with 1/2 probability, takes on a 1 with 1/4 probability, and that means it's going to take on 2 with 1/4 probability as well. So right here, this is our PMF, right? Now, our expected value of x, if we follow the formula here, it's going to be a summation over all possible values of little x, right? So we have little x, it's going to be 0 to 2. And we want to take the value of x, multiply that by the probability that it equals that, right? And so in this case, we're going to have 0 times by the probability that it's 0, which is 1/2, plus 1 times by the probability of observing a 1, plus 2 times the probability of observing 2. And so you can see this sort of feels exactly like doing the sample average calculation, right? And so then we'll get 0 plus 1/4 plus 2/4. So this is going to be 3/4. And so the idea is that if we were to run many experiments observing x here, then in the long run, the average that we should expect to see is 3/4. Whenever we have a function, just any arbitrary function h of x, the expected value of h of x can be computed by simply mapping x to h of x and using the same general formula. Now, in general, it's really important to remember that the expected value of h of x is not going to be h with the expected value of x plugged in, right? So to see what we mean again, we could come back to this little example that we have going on here, and we could take x, we could define h of x, and maybe h of x is just going to be x squared. Okay, so that's going to be 0, 1, and 4. And so then we would just plug in the expected value of h of x is going to be the summation of h of x times by the probability. So that's going to be 0 times by 1/2 plus 1 times by 1/4 plus 4 times by 1/4, right? And so now, in this case, we're going to get 1 over 4 plus 4 over 4 is 5 over 4, right? And we can see 5 over 4 is not the same as 3/4 squared, right? So the expected value of x squared does not equal the expected value of x quantity squared. We have one exception for this above rule, and that is if h of x is a linear function. If h of x equals ax plus b for constants a and b, then h of x equals, expected value of h of x is equal to h of the expected value of x. So we would specifically get that the expected value of ax plus b is a times the expected value of x plus b, okay? And this is going to be quite useful for us because linear transformations happen all of the time, anytime you say want to do a unit conversion or that type of thing. And this is going to be generally true. If you take a to be 1, then it shows us that the expected value of x plus some constant just shifts that around by that constant. If you take b to be 0, then it says that if you're multiplying by a constant, you can just multiply the mean by that constant as well. Now, in the same way that the expectation generalizes the mean for the population, we can also think about generalizing the variance for the population. Remember that the variance is the sample mean of the squared deviations, and so we can define variance in the population in the same way. So we take the variance of x to be equal to the expected value of x minus its mean all squared, right? So it's the squared deviation in expected value. Now, this is corresponding to a taking the expected value of h of x, where h of x is x minus the expected value of x squared, right? So we already know how to compute this value. But we can also make the same simplification that we saw when we were doing the sample variance, right? And so that's the expected value of x squared minus the expected value of x all squared, right? And so if we go back to this example again here, well, this first term is the expected value of x. The second term is the expected value of x squared. And so from this, we can say that the variance of x is going to equal the expected value of x squared, which is 5 over 4, minus 3 over 4 squared, right? And so then we're going to get 20 minus 9 over 16, so that's going to be 11/16. And if you work through the actual computation, taking h of x to be x minus the expected value of x squared, you should get the exact same result. The standard deviation is going to be exactly the same as we saw with the sample, where we just take the square root of our variance. Now, if we have h of x and we want to know the variance of h of x, then again, we're going to have to plug it into the definition once more, right? So the variance of h of x is going to be the expected value of h of x minus the expected value of h of x all squared, right? If it's a linear combination, what we see is that adding a constant doesn't change the variance, which is a property we saw with the sample variance as well. And multiplying by a constant is going to bring that constant out front squared, right? So the variance of ax plus b is going to be a squared times the variance of x. In general, with a constant term, we're going to think about the variance as being equal to 0. And again, if you got a sample with constant observations, then we said the sample variance there was 0, right? So this is all sort of related to those quantities we were talking about earlier in the semester. That's the very quick overview of the expected value in the discrete time, or in the discrete setting. So expectations are going to describe the long-term average for a distribution. We can think about either taking the expectation of a random variable or of its transformed random variable, and we can directly compute that from the definition. The variance is going to be defined through the expectation. It's the same expectation we used to define the variance in the sample case, and we saw that the variance of a constant is 0. Expected values are going to become second nature for you to think about, and so I'd work through those definitions and make sure they're all very clear for you. And then in the next video, we'll continue to look at discrete probability distributions.